It's time to explore TCP and UDP in the true practical networking style. Get ready to really understand how and why these two layer 4 protocols have been the workhorses of the internet for the better part of the last 40 years. Hello everyone, my name is Ed Harmouche, and in this video we'll be kicking off what'll likely be a pretty thorough series on TCP. But before we get into the depth of TCP, we have to start on the same page, so in this video we're going to be covering TCP and UDP. Specifically, we're going to be talking about what TCP and UDP are, and what they are not. Now, if you're looking for some background information before we get into TCP and UDP, we first mentioned the concepts of TCP and UDP back in our Networking Fundamentals series in the lesson on the OSI model. In that lesson, I showed you this slide, and I told you that the main purpose of TCP and UDP is what I like to call service-to-service delivery. The technical term for this is multiplexing and demultiplexing of traffic. In any case, in that slide, I told you that there are two strategies for how this is done, and that's where TCP and UDP come into play. So if you're looking for some context or background information, I'd point you to this video. There'll be a link in the description. What we're going to do in this video is unpack TCP, or the Transmission Control Protocol, and UDP, or the User Datagram Protocol, across 4 different dimensions. We'll first start by talking about 4 important differences between TCP and UDP, and then I'm going to dispel 4 common myths about TCP and UDP that I keep hearing about. With that said, let's get into the first difference that we're going to be talking about, and that has to do with TCP being connection-oriented and UDP being not connection-oriented. Now, if you're anything like me, when I first read that about TCP and UDP, I had no idea what they meant. It actually took a few years before I finally understood what they mean by this, and I'd like to communicate that to you now. What they mean by connection-oriented is that there is an official start and an official end to a TCP connection. UDP does not have that. So what that means is that before this host can send TCP data packets to the other host, it first has to send a special packet that essentially says, hey, I'd like to start speaking TCP with you. Let's start a connection. And then this host has to respond saying, cool, I'm ready to speak. And now this host can actually start sending data onto the wire. Then, once that host has finished sending the data it needs to send, it's then going to send another special packet indicating that it is now done sending data on the wire, and this host will respond saying, great, I've received all the data, I am done with this connection as well. By comparison, UDP does not have an official start or end to the connection. If this host wants to send UDP data to that host, all it's going to do is simply put that data onto the wire and hope it gets to the other side. There isn't any sort of signaling that indicates this is the start of a UDP connection and this is the end of a UDP connection. In fact, some people say that there is no such thing as a UDP connection. But in modern network engineering parlance, people refer to a UDP connection all the time. But if there's no official start or end, how do we determine which set of packets all belong to the same connection? Well, with UDP, all you can really do is define it based upon the timeout. Any packets that share the same 5-tuple, that's source IP, source port, destination IP, destination port, and protocol, in this case UDP, and arrive within the same certain time period, can all be said to be a part of the same UDP connection. Now, this timeout is not a constant value. I've seen a lot of different values from different vendors and different software. 2 minutes seems to be a pretty common one, but by no means is that a standard across the internet. In any case, that's the first major difference between TCP and UDP that I wanted to unpack for you. And hopefully that gives you a much better understanding of the terms connection-oriented and not connection-oriented than I had when I first started learning networking. Which brings us to the second attribute we're going to discuss regarding TCP and UDP. The next component that we're going to discuss about TCP and UDP is that TCP is said to be reliable. But again, what do they actually mean when they say TCP is reliable? Well, there's actually 3 subparts to what is meant by reliable, and I'm going to explore each of them for you in the next few minutes. The first subcomponent of TCP being reliable is this. TCP provides confirmation of data delivery. What that means is that if this host sends some data to this host, every time this host receives that data, it's going to send an acknowledgement saying, hey, I just received that data. This means this host knows whenever data actually got to the other side. By comparison, UDP does not have that. UDP doesn't provide any sort of confirmation of data delivery. If this host sends UDP packets to this host, it's simply going to put those packets on the wire and hope for the best. The receiving host isn't going to do any sort of confirmation that the data actually got there. That's the first part of what is meant by TCP being reliable. Now, the benefit of this is that if we are confirming every time data is actually delivered, that means we are aware if something didn't actually make it through. If this host put TCP packets on the wire and never receives that confirmation, well, that tells this host that something happened with the transmission, which means this host can then notify the application which initiated the TCP connection that some sort of error had occurred. That's useful because then the application can provide an error message to the user telling the user that some sort of error has occurred. UDP doesn't have that. Since UDP doesn't have any sort of data delivery confirmation, UDP is unaware if any errors actually happen. Meaning, if this guy sent UDP packets across the wire and something happened to those packets, this guy is not going to know anything about it at layer 4. The application might have their own confirmation of delivery built into the application, but none of that is provided by UDP at layer 4. So those are the first two subparts to what is meant by TCP being reliable. The third and final part of that is this guy. With TCP, data is delivered to the application in the correct order. So here's what I mean by that. Remember that with typical internet communication, it's not like the host is directly sending data to another host. Instead, often it's some sort of application running on this host is telling this host to put certain packets on the wire and send it via TCP or UDP. In the case of TCP, any packets that the application say to send, TCP will label with a particular sequence number. For simplicity, I'm just going with 1, 2, and 3. This sequence number can then be used to make sure that on the other side, the data is delivered to the application in the correct order. Now, if the two hosts are literally connected via same wire, then it doesn't really matter, because the order in which you put these packets on the wire is the order in which they'll arrive on the other side. But often, when you're speaking to another host, you're speaking to another host on the other side of the internet, which means on the other side of a bunch of different routers whose job it is to hand those packets off to one another to deliver them to the final host. The issue is that there is no guarantee that those packets are going to be delivered using the same path. So what can sometimes happen is maybe the first packet takes the fastest path, and the second packet takes the scenic route, and the third packet took the fast pass. And then on the other side, what you have is the packets arriving in the order 1, 3, 2, even though on the sending side they were sent as 1, 2, and 3. Now, in the case of TCP, since TCP labeled these packets with a sequence number, TCP can switch the packets around as necessary before they actually hand those packets to the application. The key there is that the other application is definitely going to receive the data in the correct order. UDP doesn't have any sort of intrinsic data ordering, which means if the packets arrived on the other host out of order and it's a UDP connection, the application is going to have to deal with that in whatever way makes the most sense. Possibly the application has their own method of sequencing, or alternatively, possibly the application doesn't really care about the order in which the data arrives. For instance, if I'm downloading a 100 megabyte file, I don't necessarily care that byte 1 gets there before byte 100. As long as all the bytes get there, I'll be happy. So that wraps up talking through the 3 subparts to what is meant when people say that TCP is reliable. Notice, however, I didn't say that UDP was unreliable. We'll talk more about that in a moment. The third major component about TCP and UDP is that TCP is set to provide flow control, and UDP does not. Let's talk about what that actually means. In the case of UDP, UDP is going to transmit its data as fast as it possibly can, whereas TCP is going to dynamically adjust its transmission rate to use the maximum available bandwidth safely without exceeding it. So let me show you what I mean. Now, if you have a situation where the host in communication are speaking across a path with pretty much consistent bandwidth availability, then this difference really isn't all that important. They both end up achieving about the same transmission rate. However, most of the time, when you're speaking to another host, especially another host on the other side of the internet, the available bandwidth throughout the path is not consistent. Often, one side of the path has more available bandwidth than the other. Or, more realistically, you'd have higher bandwidth here, lower bandwidth here, higher here, lower here, higher here, or something like that. In any case, if you were to map out the bandwidth available across the entire path in this illustration, you'd have something that looks like this. Now, with UDP sending data as fast as it can, what would end up happening is this host would look at its local connection and be like, whoa, look at all this available bandwidth I have. I'm going to send data as fast as I possibly can according to this available bandwidth. But as you can see, we have more available bandwidth here than we do over here. So with UDP, you'd have a situation that looks like this. UDP would be sending data super fast over here, but then once it got to this side, a lot of that data would be dropped, since this side cannot support the same bandwidth transmission rate. TCP, however, would dynamically adjust the transmission rate to stay within the bandwidth across the entire path. Let me show you. With TCP, you would have something that looks more like this. TCP would start out low and then start increasing the bandwidth, but once it started noticing that certain packets are dropped, it would start to adjust its bandwidth down to whatever is available for the entire path. Then TCP would bounce around at that max available bandwidth. Now, the details of that are rather interesting, and we can get into how all that works later on in this series. But for now, I just want to highlight the significant difference between flow control and how TCP will smartly use the available bandwidth without dropping packets, whereas UDP will transmit everything as fast as it possibly can. That's what people mean when they say that TCP provides flow control. And that takes care of our third major comparison point between TCP and UDP, which brings us to our fourth. And our fourth is that TCP is more overhead and UDP is less overhead. Well, to understand this one, we have to pull back something we learned about the OSI model. Remember in our lesson on the OSI model, we said that the application layers, layer 5, 6, and 7, are going to put together some sort of data that should be sent to the other side. The application layers are then going to hand that data to layer 4. And layer 4 is going to add a header to that data in order to accomplish layer 4's goals of service-to-service delivery. Then layer 4 is going to hand that to layer 3, and layer 3 is going to add its own header in order to accomplish the goal of layer 3 of end-to-end delivery. And then layer 3 is going to hand that to layer 2, and layer 2 will add its own header in order to accomplish the goals of hop-to-hop delivery. And finally, this construct over here, known as a frame, is then going to be serialized and put on the wire and sent to the other side. Now, if any of that was unfamiliar to you, specifically the terms hop-to-hop, end-to-end, and service-to-service, I'd recommend checking out my videos on the OSI model. I promise it'll be one of the best takes on the OSI model you've ever seen. In any case, going back to this comparison point, what is meant by more overhead and less overhead has to do with the size of the header being added to the data. TCP is going to add a larger header to the data compared to UDP. Let me show you. Here is what a UDP header would look like. Notice the UDP header only includes 4 fields: a source port and a destination port to accomplish the goal of service-to-service delivery, a length which indicates to the other side how long the entire segment is, and finally a checksum, and in the case of UDP, this checksum is optional. Notice the entire thing is only 8 bytes. By comparison, the TCP header looks like this. Notice it is much larger. It's actually 20 bytes at minimum, and sometimes can be larger if options are included. With options, the TCP header can be at most 60 bytes. Either way, you can see that it's adding a lot more information to each data payload. Well, that kind of makes sense because TCP has more features, and to accomplish these features, TCP has to add more information to the data. TCP also has a source and destination port, just like UDP. TCP doesn't have a length per se, but it does have an offset, which indicates how long the TCP header is. And TCP has a checksum, but in the case of TCP, it's actually mandatory. Otherwise, all of these fields over here are all new in TCP and don't actually exist in UDP. These are the fields which accomplish these features of TCP. And we're going to be looking at a lot of these fields in more detail in the next lesson. For now, I just want to really drive home the point of what is meant by more overhead versus less overhead with TCP versus UDP. So that takes care of illustrating the core attributes of TCP and UDP. Next, I'd like to discuss and even dispel a few myths about TCP and UDP. There are 4 myths that we're going to be talking through. And I'll say at the outset of this that some of these might just be subjective aversions to certain phrases. Either way, I do want you to be able to speak to TCP and UDP smartly. So with that said, let's talk about the first myth that we're going to dispel, and that is that UDP is faster. This is not true. The speed is actually identical. Now I'm guessing what people mean when they say UDP is faster is that UDP has less overhead than TCP. If that's what they mean, then they should use the term less overhead. Saying UDP is faster implies that a packet sent via UDP will get to the other side faster than a packet sent by TCP. The term for how long it takes a packet to get across to the other host is known as latency, and the latency is actually completely unaffected whether you're using TCP or UDP. So the term UDP is faster is not actually true. Yes, UDP provides less overhead than TCP, but you can't actually say a UDP packet is faster and will get to the other side any quicker than a TCP packet. So that is the first myth that I want to dispel. The second myth is this guy. TCP is more secure. And if I can be honest with you, this is by far the myth that I dislike the most. As someone who teaches security and cryptography and SSL and TLS, when people say TCP is more secure, it really makes my blood boil. TCP is not more secure. The security of both is identical. In fact, you can say that either protocol is equally insecure, since neither protocol provides any sort of security to data packets that are sent onto the wire. If you actually want security applied to your data packet, you're going to have to apply them in another layer. You'd have to use something like IPsec at layer 3, or SSL, TLS, or SSH at layer 5 through 7. But at layer 4, the choice of TCP and UDP is equal security, or rather equally insecure. So the myth that TCP is more secure is completely untrue. Anybody that says otherwise is wrong. That is the second myth that I want to dispel for you. The third myth is this one. UDP is unreliable. That's also not true. But for this one, I actually have some sympathy for it. People say that TCP has reliability, so wouldn't it make sense to then say UDP is unreliable? I get it, but a better way of saying that would be something like this. UDP doesn't provide reliability at layer 4. Saying it like this tends to give UDP a bad reputation. The odds of a packet getting through the wire to the other side are identical whether you're using TCP or UDP. The only difference is TCP actually provides confirmation of data delivery, whereas UDP does not. UDP, in fact, allows the application to provide any sort of reliability that the application needs. It simply doesn't provide any magically at layer 4 like TCP does. That's a better way of saying this myth. And that is also why I dislike the phrase UDP is unreliable, and is also why I avoided saying it earlier in this lesson. Which brings us to the fourth myth that I want to dispel, and that is this one. And I'll be honest, this one might just be a syntax issue, but one way or another, the myth is TCP provides guaranteed delivery. That is also not true. TCP simply provides informed delivery in the sense that TCP provides confirmation of data delivery. But TCP cannot guarantee that delivery of packets will get to the other side. If something is wrong with the wire between two hosts, whether you put a TCP packet on the wire or a UDP packet on the wire, the odds of it getting through or not getting through are identical. So TCP can't actually guarantee that anything is actually going to be delivered. All TCP is going to do is provide reliability in the sense of we know when data is delivered, and therefore we know when data is not delivered. TCP cannot magically make data arrive. That's why I dislike this phrase of TCP is guaranteed delivery. But again, that could just be a phrase that I personally am not a big fan of. Either way, those are the 4 myths that I wanted to talk through in this video. And that in fact wraps up the main things I wanted to cover in this lesson. In the next lesson, we're going to unpack exactly how TCP provides all these cool features we just got done illustrating. And if you understood all the things we went through in this lesson, and you'll follow along with everything we're going to go through in the next lesson, then you can safely say that you understand TCP better than most. But even then, these first 2 lessons are really only scratching the surface with TCP. There is so much more to TCP that we could be discussing. For instance, we could talk through different flags. We could talk through the sliding window. We could talk through how the checksums are actually calculated. We could discuss the different flow control algorithms like TCP Reno and TCP Tahoe. We could talk through ECN and CWR and various TCP options, some of which exist in pretty much every single TCP connection of the modern era. And I am absolutely willing to take the time to create the videos teaching through each of these additional items. But if I'm going to do that, I need you to do me a favor. I put a lot of time and effort into the content I produce. My goal is to always create the best possible training content for you. But unfortunately, that means I can't really keep up with a YouTube weekly delivery schedule, which means, regrettably, my content will never be favored by the YouTube algorithm. So if you want me to continue making this TCP series, I need you to help me blow up these first 2 videos. Do the usual like, comment, and subscribe, but also share links to this amongst your peers or post it on Twitter, LinkedIn, or Reddit, or whatever social media platform you prefer. If these 2 videos get a wide following, then I'll happily create content covering the rest of these concepts for you. With that said, we bring this lesson to a close. The main takeaways from this lesson are understanding the 4 major differences between TCP and UDP, and what is actually meant by each of them, and also understanding the 4 myths we dispelled and why each of them might be wrong. In the next lesson, we're going to go further with TCP, and I'll show you how TCP actually provides each of these features. But that's it for this lesson. I hope you enjoyed this video. Thank you for watching, and I'll see you in the next one.